condition or quasi non-expansive and so on. So we need such kind of constructive fixed point theorem. This means fixed point theorems which ensure existence and uniqueness, but for sure this fixed point theorem ensures a method, a constructive method to approximate the solution, the fixed point. This would be our aim always when we face an application. And here is the term I use for constructive fixed point theorem. It comes from a concept in the foundation of mathematics, philosophy of mathematics, if you are familiar. So in mathematics, a constructive proof means that this technique of proof demonstrates the existence of a mathematical object by creating this object, or by providing a method, an algorithm for creating the respective object. In our case, this sequence of successive approximation in many instances it provides a method of constructing the object. This is the object we are looking for, the solution. So this is a constructive and in fixed point theory, of course, the mathematical object is the fixed point, and we are interested to have as much as possible constructive fixed point theorems. Fixed point theorem is logically non-constructive. It ensures only existence of a point, but not provide any method for obtaining. So in this category, we have these famous theorems, but which are very useful in application, Schauder, Tikhonov, and many others, which ensure existence and which are important in problem as Nash equilibrium and so on. There are enough fixed point theorem which are constructive, then we can concentrate, we can focus on this kind of theorems. In my philosophy, a generic constructive fixed point theorem, metrical fixed point theorem, will have the following features. So first, as input, we should have an ambient space, which will be a metric space or Banach space, any kind of spaces, usually topologic space. As I have shown yesterday, it could be a metric space which is endowed with partial order. So partially ordered Banach spaces, partial ordered metric spaces, and so on. We have as input a mapping possessing some additional properties, but what is the most important, for this map we have a kind of metrical contraction condition. And this category, by this concept we mean Banach contraction, Cannon, Chirich, and so on. And we also mean non-expansiveness condition, quasi-non-expansive, and all conditions in this category. Then, as output of such a constructive fixed point theorem, we should have existence and sometimes uniqueness of the fixed point. We should have a method for approximating the unique fixed point or the fixed point if there are many. And also we should have an error estimate, and also, if possible, rate of convergence, information about rate of convergence, information about stability of the method. As beautiful model, Banach contraction principle is following all these requirements. And now we are familiar with Banach fixed point theorem. Let's look at it. We have a setting, complete metric space, XD. We have a mapping T. Nothing is required, no additional property. By the way, if you look at the original Banach fixed point theorem, he asked T is continuous, but at that time, when he wrote his dissertation, there were not yet established the concept of continuity for an operator. The continuity has been defined only on real line, so not in a function space. And he said T will be continuous, but we know that any contraction is continuous. And if we have this contraction condition, for sure T is continuous and we don't need to impose. So all items in the output are here present. T has a unique fixed point. We have an iterative scheme, the Picard iteration, which converges to this unique point, and we have this rate of convergence I mentioned before when I presented Banach contraction theorem. And if you remember, I said this is a priori error estimate for n equal I equal 1, and we'll have xn, distance by xn, and x star is less than a over 1 over a. A is the contraction coefficient, d of x0, x1. This is the a priori, and a posteriori we'll have here dxn xn minus 1, which we get by taking I instead of I will set n and so on, but and n1, but I don't write this. This will be a posteriori. I have shown you what is useful having this, and the last condition, this one, shows that the rate of convergence is linear, is 1. This means the Picard iteration has linear convergence, rate of convergence. So I'll speak here about some aspects related to applied iterative schemes. I just mentioned computability, but I'll discuss about rate of convergence of an iterative method and stability of the iterative methods. And I'll consider some context for one-step iterative schemes and for multi-step iterative schemes. In the category of one-step iterative schemes are all with these methods we have seen. I include in here Newton method, which consists of the Picard iteration when T, which is called iteration function for Newton method, has this expression I mentioned before. Krasnoselski, Mann, Ishikawa, and so on. There are some authors, they call this, if we start by an x0 in x, and x n plus 1 is like here, xn plus t of yn, lambda, and then yn it's, let's say, xn plus theta This is a two-step iteration scheme. Why? Because we have involved xn plus 1, xn minus 1. So the difference between this is 2. So this is a two-step. But there are some people, in the absence of this term, they call such an iterative scheme is two-step, is not correct. So two-step means this. We have three iterations, three consecutive iterations. The difference between the greatest one and the smallest one is 2. So this is the difference between n plus 1 minus n minus 1 equals 2. So this is the reason it is a two-step iteration scheme. We have also this kind of multi-step iteration schemes. And this iteration scheme is related to a fixed point by another Serbian mathematician. He gave a generalization of the Banach space of Banach contraction, Banach fixed point theorem, in a very interesting way. He considered T defined on x to the power k to x. K is greater or equal to n and is integer, of course. And he wrote the definition in this way because we are in tk, t of x1, x2, xk is less than alpha 1 distance between x0, x1, alpha 2 distance between x1, x2, and alpha will be distance between xk minus 1, xk, alpha k, and this constant, let's say alpha, is less than 1. Then he proved then T, if X, D is complete metric space, then has a fixed point, a unique fixed point, in the sense that T of x k times x star is exactly x star. Very nice theorem. And look, if we take k1, what we get? If we are in the situation k is equal 1, we get distance between t of x0, t of x1, we use this notation, is less than alpha 1 distance between x0 and x1, and it is exactly Banach contraction. So in this context, we have this iterative scheme. So k step iterative scheme, which is known to converge to this fixed point. I'll refer, for those interested, in this book I sent you something with it iterative. I don't know exactly what is the title, but you should have this book. Here, this topic is treated in much detail. So let's go further. So we could have one-step iterative schemes. We can have multi-step iterative schemes, but for all, the main numerical features are these ones. So computability, rate of convergence, stability. Computability, you can imagine what is. I don't insist on this concept because it would mean our algorithm is implementable, so we can implement it in a certain software environment, and then we have convergence. This algorithm is finite, is not ambiguous, and is effective. These are the properties, main properties of computability. If you are not familiar with this very interesting topic, which is complexity. Did you hear about complexity theory? Not complex analysis, but complexity theory. It is in computer science. It's about the complexity of an algorithm. This means how complex it is. There are some problems in graph theory, for example. Graph theory. Did you study graph theory at the university? Yes. Okay. In graph theory, there are some famous problems. Traveling salesman problem, for example. This is known to be a non-polynomial hard problem, in the sense that if we have
we have in linear programming.
Oh, in linear programming, of course. Linear programming is also this kind of yes. So this is also this means in fact implementability, and for this problem it is known if we have a graph with, let's say, 6 vertices, and we need to solve the traveling salesman problem, we'll need 6 factorial ways to check which is the optimum. So this is incredible. This is huge number. You can by one method, by the, how is called this method, brute force method. This means to check all possibilities, but there are others. So this is a hard non-polynomial hard problem. Coming back, so this would mean computability. We don't consider this, but some iterative schemes can be easily implemented in a certain computer environment, and some of them not. So if we have such a scheme, we can implement it. We have an algorithm. It is very natural to answer these questions. How can we find an indicator for one step, single step iterative scheme, which should characterize each rate of convergence, speed of convergence? To have some tools to compare 2 or more iterative schemes, like in our case. We had it iterative scheme corresponding to TT, to T3, how we can compare these two and choose among them which one should be used in application. And this problem leads to a very important concept in numerical analysis, the concept of rate of convergence, which is also called sometimes order of convergence or speed of convergence, and there are many other terms that are used, but this information analytically is obtained by means of this rate of convergence I have shown you before. So if we are in the presence of such a rate of convergence, we had this for contractions. So this we are done. We have the information for this how we can stop this, and the second one, this formula, if you remember, is about the rate of convergence. So error estimate rate of convergence depends how we can obtain. I would speak of some facts I included in this paper from 2016, lot of time, where I discussed on a notion of rate of convergence which is useful in many cases in fixed point theory. And I'll have some information maybe new for you. In this numerical analysis, there exist several concepts of order of convergence. I start by this one, which is the oldest one. We treat it in the general case of a metric space. We have a metric space. We have a sequence xn, which is in general generated by an iterative scheme, and we know it is convergent to some limit x bar, which is the solution of our fixed point problem, solution of our original nonlinear functional equation. And this is the error estimate. If we have such an error estimate where alpha n, it's a sequence of positive real numbers which converges to 0, then this error estimate is very useful. What it says for us? The sequence xn converges to x bar at least as fast as this sequence alpha n of positive numbers converges to 0. There is an old notation for this kind of error estimates with big O. So this means this distance is O of alpha n. This is one order of convergence. This order of convergence comes from these times, so 135 almost years ago by Pringsheim, Abel, Adamar, and so on. They introduced this concept and also the notation. And it comes from the theory of series. I told you about a series of positive terms, and here I can speak in more detail because I presented some parts of this talk in Ghaziabad. He was attending. He's the only one, I suppose, who attended this. But there I could speak just a little bit about this. Here I can afford to speak more. So we have two series of positive terms. They are convergent. They have some S and T respectively. And this, if we have a convergent series, we know that for sure UN converges to 0 and Vn converges to 0 as n tends to infinity. And if we have this inequality between the terms of this series, we say that the first series, sum of UN, converges more rapidly than Vn, or that the series Vn converges less rapidly than Un. This was the concept introduced by these mathematicians, and this inequality implies actually that this the sequence UN and this sum of partial the sequence of partial sum we call in the theory of series converge or approaches their limits, which is 0 and s, faster than the sequence Vn and the partial sums Tn converge, approach their limits 0 and t respectively. And this inequality can be in fact written in this way, is exactly what we had. So un minus the limit less than a constant Vn minus each limit, and this is exactly expressing that this has this form, and the sequence alpha n is this one, and this, as I said, this expresses the fact that the sequence xn converges at least as fast as the sequence Vn to their limit. This is one of the most common form of the error estimates we can find in literature for iterative methods. Is not the only one, because there is another one which is usually convenient for Newton type methods. For sure you have studied numerical analysis. So in numerical analysis, we usually have these Newton type methods. They are more elaborate Newton type method than the Newton method itself. And this rate of convergence has been introduced in this year by Voigt. Voigt is a German name, but he's in USA, in his PhD thesis from 1969, and maybe I've mentioned in a previous talk this beautiful book by Ortega and Reinbold, which is a fundamental monograph on iterative solution of nonlinear equations in one or several variables, which is old book but still of actual. I don't know about a new edition of this book, but it is extremely nice, and it is useful even if not all methods are fixed point iterative methods in this book, because most of them are of Newton type and many other gradient type, projection type, and algorithms which are not necessarily of this fixed point type. And this rate of convergence is totally different defined. Look, we have a sequence xn which is generated by a certain iterative method, and this sequence converges to the limit x bar, and if we have this relation, so limit of dxn plus 1 x bar over d of xn bar to the power r is a certain finite lambda, then we have the following concept. R is called the rate of convergence of this sequence. Please remember, we had for Banach contraction mapping theorem, we have this rate of convergence. We can do this, and you can see that this is can be written in this way, and this is xn bar xn star to the power 1 less than a, and this is very similar